Yeah, thanks to CASC and Priyanka and other organizers for inviting me here. I'm Sivabalan. I'm part of LinkedIn infrastructure group. Today we're going to talk about Ambry. So LinkedIn Scalable Geo-distributed object store. So today's agenda is going to be, I'll start with media significance in today's world. How did media infrastructure look at LinkedIn like 3 years back, before Ambry? What are the motivation and design goals when you started building Ambry? What are the APIs we support? Architecture at the high level and a couple of selected internals. Some performance numbers, how to get started if you're interested in Ambry. Media is pretty ubiquitous everywhere. There are so many applications, so many products whose bread and butter is just media. Media includes pictures, videos, virtual reality going forward. So this holds good not just within LinkedIn or even across the web. So media is going to be is an important player in causing user engagement and causing virality. So to support such media use cases, you need a world-class infrastructure. Our group at LinkedIn is building one. So let's see how media infrastructure looked at LinkedIn a couple of years back. So there were so many applications which were using different kind of stores for their media use cases. We have a key value store called Voldemort. Some of the applications are using Voldemort to store their media. We have an Espresso, it's a structured document store. Some of the applications within LinkedIn are using Espresso for their media use case. Some of them are using Google App Engine, and some of them are using Media Server. So Media Server is the one which was actually built to support media use cases within LinkedIn. It's a bunch of filers put together. We had Oracle to store the metadata for looking at the actual files. We had a lot of issues with the Media Server, which I will be going through in the future slides. So definitely this called for a unified solution. We looked up for the available options. So first question which might come to your mind is, why not use any of the available file systems out there? So we felt like most of the file systems out there had certain extra capabilities which are unnecessary for an object store. For example, they had an hierarchical directory structure, and then they were mapping each object to a separate file. So this involves at least a minimum of 3 disk read per lookup or per read of an object. So this adds a lot more latency to your fetch. The next question is, why not key value stores? Like 3 to 4 years back, there were a lot of key value stores which were pretty good performance. Why not use key value stores? Key value stores basically are not designed to support very large values. So I'm talking about medias to the order of, let's say, a few megabytes or even a few gigabytes scale. So some of the key value stores might end up copying at multiple places, so you might eventually run out of memory. And most of them lack streaming and chunking. What do I mean by streaming is, let's say you have multiple layers in your system. Let's say you have 3 layers. The middle layer, after receiving the entire block, it might process something and then send it to the next layer. But then if you're going to model in such a manner, then your throughput and latency is going to be affected a lot. What do you mean by streaming is, let's say if someone is trying to upload a 1 gig object, for example, the middle layer should try to get some amount of chunk, let's say a few megabytes, try to process it, and then as and when it processes it, it should just move it to send it to the next layer. So these were the lacking points in the key value stores. So we built Ambry for the media use case on LinkedIn. There were certain design principles which we considered when we started building Ambry. The first and foremost is low latency and high throughput. This is pretty much a requirement for most of the data systems, and especially for media use cases. This is very much necessary. We have Ambry is a log structured system, so you just append to the end of the log. This gives you a very low latency for writes and high throughput for large objects as well. I will cover up this point later in the slide, how do we achieve low latency and high throughput. Unstructured content. Ambry is designed specifically for media use cases, as I was telling. It's just a raw byte. There's no secondary index or anything of those sort. But then it supports immutable content for the data. Geo-distribution. Again, since we are talking about media use cases, let's say you upload a picture in your social network and then you share it with your network. Quite possibly, one another person at the other end of the globe is going to try to do the picture. If you don't if you don't have geo-distribution, your latency is going to get affected. Let's say you're planning to store video ads in your content store. Let's say your system becomes unavailable when you're trying to play ads. Try to think about the monetization aspects of how it's going to take effect. We had scalability in mind from the ground up because we had a lot of issues with the previous system which I was coding, the media server. With just a bunch of filers, we tried to tweak in, try to add a bunch of nodes, try to patch it out, but then it's not scalable beyond a point. We couldn't live with it. Scaling Ambry is as simple as adding a bunch of nodes and then adding new partitions to it. I'll come back to what partition being the later part of this talk. Low operational overhead. You could design a system which is perfectly, perfectly designed, very well performant. But then if you add a tagline saying that it's a little tough to operationalize, then no one is going to take your system for that matter. Operationalization is very important, especially in the infrastructure world. We had a lot of tooling built around Ambry for the operation aspects of it. Active setup. We have a lot of replicas for each block we upload. There's no master or slave concept in Ambry. We specifically chose this design because you don't need to maintain a lead reduction algorithm or the slave doesn't need to catch up with the master every time. So active setup, which means that the writes and reads can go to any replicas for that matter. Cost effective. Since time and again we are talking about media use cases here, as media becomes old, it also becomes cold. What do I mean by cold is that the read QPS for your data gradually decreases as it increases the age. So you can't afford to store your data in very expensive systems. Ambry is very much deployable in just commodity hardware or just JBoard system. You just put in a bunch of disks together and just deploy Ambry in it. What are the use cases in which you can use Ambry? To store a variety of objects, documents, slides, PDF, anything for that matter. Variety of media files, like pictures, sounds, videos. It could range from few KBs to few gigabytes. You can store backups. Most of the companies out there have databases for their real-time systems. So definitely everyone needs a backup. Even there is a requirement from Espresso within LinkedIn that they need backup like once a day. So backups take huge spaces. If you're just going to store in a file, it's overhead for you, and then you need to delete it after a certain time. So Ambry actually provides a TTL for you along with, when you're uploading, you can set a certain expiry for your objects and then you don't need to worry about it. You can set an expiry for 2 weeks and then after that, it's automatically deleted from Ambry. Range query support is very much important for videos because let's say you're trying to view a very large video, 1 hour video. If you try to jump after half an hour, there's no point in when your system fetches all the entire chunk of data. You just need to start streaming from the 1 hour. What are the APIs with Ambry support? APIs are pretty simple: post, get, and delete. Post, you just upload a content. Along with the content, you also specify certain properties along with your blog, and then we return a handle to it. Just remember that Ambry is not a key-value store. So keys are generated within Ambry. So we return a handle to your object. You just upload a content and we return your handle. Using that handle, you can call get or delete to it. Get are of 2 types. You can directly fetch the content using get blog, or you can call get blog info. Get blog info is going to return you the properties which you upload, which you send in during post, and then user metadata. User metadata are a bunch of or just arbitrary metadata which the user wants to store along with the blog. Ambry as such is not going to interpret the user metadata. Delete. Delete is self-explanatory. Just pass in the handle which you return during a post, and then we delete the content from Ambry. Let's move on to the architecture of Ambry. So it's a 3-tier architecture. The middle layer is the front end. The first layer is either the CDN, can directly contact the front end. Or you can have an embedded client library which speaks with your front end. Front end speaks HTTP, so it's easy for you to access from any language. Front end, I will go over some more points about front end in the next slide. And then we have a cluster map. Cluster map is used to state which stores the actual state of the cluster at any point in time. And then the last you have the data layer. Data layer is where the actual data is stored and retrieved. We have a native replication in place, which makes sure that all replicas are in sync with each other all the time. Front end. As I told, it speaks HTTP. It's completely stateless. So if at all one of your front end crashes, it just asks.
Sorry to interrupt. What is the consistency model for replication in Ambry?
It's eventual consistency.
Eventual. Okay. Thanks.
Front end is stateless. So if at all one of your front end goes down, it's as simple as you just bring up another node and then deploy front end and then bounce it back. That's it. It has a pluggable validation and authentication service. Let's say you have your own security mechanism to be in place for all the requests which are reaching your system. You can have your validation service plugged in. You can have your authentication service plugged in. And then pluggable change capture. Let's say you have your own notification system. That's a pretty good use case revolving around this. For example, in LinkedIn or even Facebook profile pictures, there are multiple pictures generated for a single picture you upload. Because based on the intent of the request, let's say someone is searching for your name in the search bar, your picture will be shown in thumbnail view. If LinkedIn is proposing you or suggesting you that people you might view on the right-hand column, it might be showing a different resolution of the picture. If you go to someone's profile, it will show a different resolution. If you click on the profile, it will actually show the original image. So for every picture someone is uploading, there will be 3 to 4 different variations or different resolutions of the same picture uploading. So you could plug in your notification system. You don't want to affect the latency during synchronous during your upload. So you just upload one block to Ambry, and then you just plug in a listener. Once a block is completely uploaded, then the listener will trigger generating few other assets for the same image. And then front end embeds a router which actually does the routing for you. We can look at what are the other characteristics of the router. As I told, router is a main library which does the routing for you, which takes care of carrying on the operations on your behalf. One thing which I want to emphasize here is that you can use the router library embedded in the front end as a service as such, but then if you're very particular about performance and if you're okay implementing some of the features offered by the front end, you can embed the router library in your service as such and then reduce one hop. So directly your service is going to interact with the data nodes without interacting with the front end. Proxy request. Let's say there are multi-master services. One service is trying to upload in one data center, and then immediately another service is trying to fetch from a different data center. Router has a capability to, let's say you try to look up in local data center. If it doesn't have the block, it goes cross-polo. You can configure all these according to your consistency model. Zero cost failure reduction. We don't have any heartbeats per se to direct down resources like nodes or disks for that matter. We rely on the actual request to detect if the node is down or not, and then try to avoid sending further requests to it. Data layer. This is where the actual data is stored and retrieved. Pretty synonymous to any data systems. We have partitions and replicas. Partitions are a bunch of blocks put together. We have multiple replicas for durability and fault tolerant purposes. Ours is the log structure. This is how a log looks like. In simple terms, we pre-allocate a very large file, for example, the 100 gig file, and then as and when new uploads are happening, you just append to the end of the log. I'm just simplifying a lot of things for the purpose of this talk, but an actual record will have some metadata associated with it. And then we have index segments, which is used to look up the actual log in the log. During upload, you just make an additional append to the log, and then make an additional entry in the index segment saying where exactly the log is present. During lookup, during a get, you will look up an index segment and then try to go and fetch the actual log from the log. So there are two different types of record which you can find in the log. One is put record and delete record. Whenever lookup happens in the index segment, we always go in the reverse chronological order so that you end up encountering a deleted record before a put record. Some of the key optimizations which were done here, which helps in low latency, high throughput, which I was telling. Since ours is a log structured system, all the lines just happen at the end of the log. There's no sync involved. We try to avoid unnecessary movement of actual data. We have a native replication, as I was telling. So the actual data is transferred to a node only once most of the time. It's not like a key-value store. You just get all the differences and then just show it to the other end. And then, so we try to do most of the metadata exchanges most of the time. Only when the actual data is missing, the actual data is being transferred during replication. Index segments used for the lookups. Even though we memory map the index segments, we also have bloom filters on top of it, so that we try to avoid going to the disk most of the time. And then we rely on OS page cache for serving hot logs. Zero copy for gets. This is very important. For example, whenever someone tries to read a particular block, we directly send the data from the disk to the NIC buffer, bypassing the user space. We don't copy the data to the user space at all at the storage layer. Let's see how performance numbers look like in Ambry. It's a beefy single node config. We have 3 different types of workload: read, write, and write only. We use fixed size objects in our testing. And then our workload is pretty much like making random reads. Just want to emphasize the point here again. This is a worst case scenario, because in real world, as we are talking about media use cases, the media access pattern is pretty much like most of the recently uploaded blogs are actually frequently accessed. So as the data gets older, the QPS for those are pretty low. But then we have done the performance which we have done is pretty random reads. So this is a graph showing throughput, how throughput of Ambry looks like. X-axis as the block size gradually increasing, and then the y-axis as the throughput in megabytes per second. As you can see, for large blocks, we pretty much saturate the network. The orange dotted line here is the network bandwidth. For the read and write use cases, we actually pretty much saturate the network. For read-write, we saturate both the inbound and outbound link, and that's why you see the 2x in network bandwidth. But then the interesting point is for the smaller blocks. You can see for writes, since it's a log structured system, writes again pretty much saturate the network for even for smaller blocks. But for read-write, and especially for read, the throughput drastically drops. The reason is that there are a lot of disk syncs involved during fetching the block. So to confirm our theory, we used Bonnie++, which is a micro benchmark for measuring disk performance. We realized that, for example, for a 50 KB block, almost like 94% of your latency is incurred due to your disk sync, and the actual data is taking like 6% of your latency. Again, I'm reiterating a point that we did a random read completely. So if you're using it in a real world, most of your GET requests are going to actually go to the reason block. So you'll be the latency is not going to get affected as much. Latency, x-axis, you can see the block sizes, and y-axis latency in milliseconds. For large objects, it scales propose. Yeah.
So your talk is talking about geo-distributed data store, right?
Yeah.
So would you elaborate a bit more on how your benefits of the geo-distributed? In other words, with regards to all these parameters, if using your store and the different nodes or different geographies, is it better or achieve better results here, or what do you mean by your geo-distributed? Because I was expecting to hear something about geo-distributed, and then hence you have something.
Okay, there are a couple of aspects in geo-distribution. For example, as I quoted earlier, let's say you upload a blog in one data center, and then you share your content with someone else. So let's say someone else or some other server is trying to fetch the same blog in some other data center on the other end of the world. If let's say the replication hasn't caught up by then. Oh, sorry. Yeah, so we have multiple replicas, so we have replication in place. So if someone is trying to access from the other end of the world, they will be fetching from the local data center rather than going cross data center. So they will be able to fetch it in a pretty good latency rather than going cross data center.
But the other data
Yeah, Ambry is an infrastructure layer. It's an object store which gives replication for you for free. You don't need to do anything for it to be able to do.
So I don't need to take the time, but if you could add a little bit more on what is it about the geo-distributed way that will show that yours is better versus the key values.
Okay, probably I will take it up offline or at the end of the talk. For large objects, the latency scales proportionally with the blob size, as you can see here. For small objects, again the same point which we saw in the throughput, the write is scaling proportionally to the blob size, since we just happened to the end of the log. But then for reads, it's taking a hit on the latency. Like it's majorly dominated due to the disk save.
This is quite high. What would be the reason? Is it because you have so many blobs in this same node?
Sorry?
This latency is quite high. Could you know what is the reason? And then the reason is quite high.
Okay, so you're saying for let's say for 1 KB block, the latency of let's say 10 or 12 milliseconds is too high.
Yeah, we have so many blocks on this node. What could be the reason?
Can you come again?
Do we have so many requests coming in at the same time, or what would be the reason?
So this is a non-queued example. Yeah, so this is non-queued, queued at 1, and the access time is basically dominated by media time. And he's working on the HDD, so there is everything media time is associated. If you get much smaller time, it will flash.
Oh yeah, so we don't have any caching layer on top of Ambry at all. So you can't exactly compare with any other key value store which has a caching. So these are just predominantly from the discrete. But then if you want to, you can add a extra caching layer on top of it. So most of the reads will just be read from the memory. Our roadmap, we have a couple of exciting projects coming on the way. Quota management. As of now, we don't throttle any of the users or servers for their requests. Authentication and authorization. We don't have a pretty good story defined yet for Ambry for authentication or authorization. Third one is erasure coding. As data becomes old, it's going to take up a lot of space and the read period is going to go down. So there's no point in actually storing every data and every replica which you have. So erasure and coding is a pretty good project so that you store in less number of replicas, but then you're going to retrieve the same durability. Deduplication. Since the media use case, there are very high chances that same blob is uploaded by multiple people or multiple users for that matter. Deduplication will actually save you a lot of spaces for that matter. Dynamic cluster management. We are able to have a good story for dynamic cluster management for now. So how to get started? Ambry is open source. We open sourced it like 2 months back. We had a paper in Sigmod as well. We have a LinkedIn blog of that. We have a quick start in our GitHub wiki. We had open source in mind right from the starting, so documentation is pretty well done. If you have any doubt in getting started, or if you feel does my use case fit in Ambry well, you can definitely send a mail to us. Yeah, we can open questions.
So the only way to access object from Ambry is through the blob ID, right?
Yeah.
So do you support like search on the metadata? For example, if I want to like look up all the videos posted yesterday for users in California, something like that.
Okay, so one suggestion I would have is again, we don't want to add too many functionalities to Ambry per se. So this is very much designed for immutable use cases. So one suggestion is, as I was telling you, you can plug in with the notification system. You can see that if you have Kafka, and then you can send notifications to Kafka to Hadoop, and then you can process. You can have a Hive query to run over Hadoop, and then you can retrieve the blob IDs and then try to fetch the blob from
In that case, like I can do the multiple get. I can send a batch of blob ID and get a batch of object back. Or...
Yeah.
do you have any comments relative to, as you were designing Ambry, do you have any comments relative to S3? Because S3 had a pretty, they have been doing object storage since 2006.
Yeah.
So as you were designing this from the grounds up, how were you trying to improve and differentiate yourself for your internal applications?
Our API is pretty much similar to S3. Even some of our features or roadmap is actually what S3 is driving us. We haven't actually done a pretty good benchmark against S3, but S3 is not open source. So if you want to have more tuning knobs or more controlled environment, so Ambry is going to be the use case for you.
The index that you show for the files that you show, is it in memory or in disk?
The recent index segment is in memory. The older index segments are memory mapped.
Okay, so how do you read the index? Each time the node goes down?
So indexes are persistent.
Okay.
So you have multiple index segments. Only the recent index segment is in memory. But the older index segments are persistent, but then we memory map it. But then we have bloom filters as well, so you don't actually go to the index segments every time.
You had an Ambry ID for an object. Does that stay live for, is there a different time period for that ID? Or can
Sorry?
How long does that Ambry ID stay valid?
It's just infinite until you delete the block. Until you issue a delete.
So these are not recycled at any point in time.
So are they effectively like a UUID then?
Yeah.
There is no concept of expiring, you can configure.
Yeah, I didn't mention, right? So you can have during upload, you can mention what, if you want to add, you can have an expiry to it.
So another thing is the ID, you said ID, we don't specify the ID to store an object.
Yeah.
So then how do we retrieve based on the ID created by Ambry? Or?
Yeah, so if you see here, during post, we return you an ID to your content. So we return an ID to you on upload. And then you use that ID during your get or delete. That's like unique identifier for the content you upload.
What's the size of the ID? Is something rememberable, readable?
It's like 16 bytes if I'm not.
Because
But that's actually, again, the ID generation, it's pluggable. So if you want to have your own ID generation, you can define your own ID generation. It's just factory.
we can define.
Yeah.
Just like MongoDB, it returns an ID internally, and also we can have our identification to retrieve the data. Is there any limit on the size of the ID we can store?
Number of entries?
No, the size of the key. If you want, we can choose our ID, right?
It's not choose your ID. So you can't. So it's not a key value store. It's a handle store. But the way we generate the ID, we have a default implementation. But then if you are deploying, if you don't like the way the default implementation, you want to have a custom way to generate an ID, you can give your own definition to it. So the Ambry anyway is going to generate an ID and give it back to the user. But then if you want to tweak the Ambry, then you're going to do it.
So as a user, you know, you can implement a different algorithm for ID generation. But out of the box, you will be given an ID that Ambry generates, and it will be whatever the size is.
Yeah, the limitation is some of these key value stores like Redis, React, the size of the key. So that's why I was asking.
Oh, but then here you can override and then define your own size if you want.
Whenever we want to do, we create a compound ID, session ID, some customer ID, then we put a long one. That kind of limitations does it have something like that. That's what happens. Sure, for sure.
Given the size of the objects, does it make sense to have a batch to it?
Sorry, batch?
Yeah, because you're basically did that to manipulate very large data, big videos. So you post, get, delete, what about batch? Would you update a certain segment of video or any binary data without having to re-upload, restream everything?
If I'm not wrong, your question is, do you have a batch upload?
A batch.
Oh, iterative. No, it's just an immutable. It's just an immutable store. you can't update the blob at any point in time.
Right.
If you need it, then you probably need to delete the old content and then issue a new content, new upload. But I would suggest you, if you're pretty much doing a lot of updates to your content, then Ambry may not be a pretty good fit for you.
Well, let's say, for example, we have SoundCloud type of data where people can just modify the binary data. You can store it somewhere else, but it would be interesting to be able to.
Okay, yeah, that's what. So if that's going to be rare, then you could delete the previous content and then upload a new content.
Right.
But Ambry is just for immutable data. You can't delete.
Right.
So unstructured data usually gets replaced rather than you go and modify the content itself. So one of the common use cases we have is, for the update issues that we talk about, we usually have some kind of a key value store, or maybe a relation database or something, which eventually will have a field for the ID for the object that is actually stored in Ambry. And what Ambry really provides you is it will be able to stream out the data and all the optimizations that Ambry has for supporting large objects. That's what you get. It's the database or the key value store by now.
What were you using before?
So previously we had a very we had a system with a bunch of filers, the media server system that we talked about. There's a bunch of filers, with, every object would go into the filer as a separate file. And then there was a
reference in the database.
then there was an Oracle database or something to store the data. And every time, because of the metadata lookup, you have a CPU spine and things like that.
So do you plan to add your cache layer like on Ambry or?
Yeah, we don't explicitly add it, but then if in your deployment, if you want to have a caching layer, yeah, you're able to add it. But then Ambry as such, it doesn't provide any caching. So, as I was speaking, we rely heavily on the OS page cache, and if you're pretty much like a media-driven use case, then most of your blobs are actually served from the in-memory or OS page cache. So we didn't find the need to have an additional caching layer. And then from LinkedIn, we have a CDN layer, so most of the hot blobs are actually served from CDN itself.
Sure. When you replicate data across different geographical areas, right? You just replicate everything, or it's based on the rankings, saying, okay, this person is being viewed so many times in a week or month. You give preferences to the ranking of the person whose data is being looked at in different Mainly I'm looking basically, are you basically replicating everything? If yes, then how does it help me if I want to make sure that certain data set is available readily? For example, I loaded a data right now and I have somebody who view my profile. Within a second he has that. And that person happens to be in Australia.
Okay, for now, every data is actually replicated to every replica. If you want to have customizable based on, let's say, user or service or organization, then probably I couldn't think of a readily available out-of-the-box solution, but you can tweak in and then try to define replication per partition. So for different partitions, you can define different replication schemes.
The framework that you're using for cross data center replication?
No, it's a native replication which Ambry has on its own.
What is the native?
Okay, so apart from the index segment which I was telling, we have a concept of journal. So what journal means is, it actually going to contain the same content as the recent index segment, but it's going to be keyed on offsets. So let's say this is the latest view of the log, at the end of the log, of one replica, and then that is the latest view of the log in the other replica in the same partition. So as of now, you will see like 6 logs out here and 6 logs over there. We don't care about the ordering per se. I could tell you how it's going to matter. So during replication, what happens is, every replica maintains what is the last known offset that I knew about everyone else. So replica R1 knows about R2 until 690. So during replication, it asks what are the new blobs that are come to your store. It returns just the blob ID information, not the actual blob. And then in third step, it filters out what are the blocks it already has, and then just asks for the actual block content. And then the second RTP, it returns the actual block, and then it updates the local store with that block. So here as well as here, especially here, there are chances that the actual block is being replicated from different replicas. So we don't actually replicate over here.
Guys, let's wrap up the meetup now. You can always talk to Shiva after you do raffle. Thank you, Shiva.